Listening today. It's always cool when somebody is willing to listen to you talk about what you do and what you love. So when I was thinking about what would be interesting to teachers, I have this project that I'll talk about, which is building space computers, and it can be interesting to some students, not all students, but it might be more interesting about what can be done in Montana, because I think sometimes there's a perception that if you want to do something meaningful, especially with like technology and aerospace, you need to go to Silicon Valley or you need to go to Austin or Denver. And so maybe the message might be, there is stuff going on in Montana, so you don't have to leave. You can come to Bozeman or one of the other places where we're doing this. All right, so a little bit about myself. I was born and raised in Billings, Montana. Went to West High. Anybody else? There's a few out there. So I kind of had the high school experience of, I was in the honors math and science classes, so I was kind of friends with the nerds. I was in remedial reading and English, so I was friends with all the stoners. And then I played sports my whole life, and so I was friends with all the jocks. So I kind of had these three desperate friend groups that I kind of maintained till this day. I chose to go into electrical engineering for the same reason that most people that come to MSU tell us is why they chose it, which is they just happen to have a family member or they knew a friend of the family that was in that. So I had an uncle who went to MSU many decades ago, became an electrical engineer. So my oldest brother chose electrical engineering. So then my middle brother chose it because the oldest brother did, and I chose it because the middle brother did. Didn't have a clue what it was. I lucked out that it was interesting to me, and I stuck with it. I went to work for Hewlett-Packard graduated from MSU back in '98. Went to work for Hewlett-Packard in Colorado, and there, it was really cool. I worked there 8 years, and I got to build test equipment for computing companies. So Hewlett-Packard back in those days was a huge, huge company. They made test equipment for the big, huge computer companies. So our customers were like Intel and AMD. And it was really an awesome experience to learn what that industry was all about. And I just fell in love with it. Computers, they're so enormous what goes into building those little chips that are in all of our devices. And it was just super cool seeing it. So then I learned about how to build circuits and all that sort of stuff. Just like every other big company, they pay for you to take classes nights and weekends. So I right away went and started taking classes at the University of Colorado to chip away at a master's degree. Then after I got that, they were like, hey, do you want to teach a class? And I was like, no way. So then I taught a class, like a night class, and then I fell in love with teaching. I was like, this is sweet. So then I said, okay, is there a way that I can combine teaching with the engineering stuff? I was doing it at work. And it was like, well, professor kind of looks like that. So I just kept taking classes and got my PhD. And so then after about 8 years, we had our first daughter, and it was like, well, maybe we should get a little closer to family, not too close, but where could I work in Montana as a professor in electrical engineering with a focus on computers? Now, I don't know if you know this. If you know how many jobs there are for that? There's one. There's one job that does that in the state of Montana, and it just happened to be the guy who was retiring, Fred Cady, and he was a former professor of mine. I lucked out, got it, moved here. 19 years later, I'm sitting here going, holy cow, what a ride. It feels like I just started at MSU, a couple years ago, but I did not. Okay, so my interest is in the area of computers. And so I always think about, like, how do you motivate your interest in people? It's like, computers are pretty easy to motivate, right? It's like, could you imagine your life without a computer? But one of the things that's interesting is that personal computers, like the laptops and workstations that you have, there's about 400 million of those sold every year. So there's quite a few, like more than one for every American. Obviously this goes global, but there's a lot. Smartphones are more in the 1.5 to 2 billion a year, okay? And that's a lot of computers. But one of the things you don't think about with computers is that there's another class of computers that is all the little computers that are in the microphones and this little controller and in the owl and all these little devices, and they're called embedded computers. There's 30 to 40 billion of those sold every year. Now that's every year. And there's only 8 billion people on the planet. So you think about the number of computers that are generated to support the life that we have. It's just remarkable. So anything that can basically improve computers would be of benefit to somebody. So that's kind of what I wanted to do. So I was like, I'll try to improve computers, okay? So I came up to MSU and I'm like, all right, everything with computing it follows this law called Moore's Law. So there's a guy named Gordon Moore, he started Intel, and he made this observation that every 18 months, the number of transistors on a circuit chip would double. Transistor is the building block of a computer, it's basically a switch. And that held true for 40, 50 years, all the way from the 70s all the way until today. So all you really had to do was wait for smaller transistors to come out, more transistors on a chip, and your computer would naturally go faster. And so it's kind of a cool trend to ride. So then if you look at this, you start back with like, how many transistors were on the first computer, right? It was like, not very many. First transistor was invented in 47. The first microprocessor was in the 70s, and it was 2,300 transistors. Today, the largest single chip, the transistor count on it is 208 billion. So the predictions are that we will surpass 1 trillion transistors by the end of this decade, okay? You get to the point where you can't count them in a lifetime. So it's totally abstracted. It's just remarkable to think about what is happening. So the problem is this: every time you shrink the transistor, computers go faster, except they stop going faster. So what ended up happening is that all of a sudden the computers weren't getting faster because you put more on there and they got too hot. And so you were like, well, they're going to melt themselves, so I got to do something. So then they would have to slow them down. And this is right when I became a professor. So I was like, what a sweet job transition to basically start this new career in computers, and all of a sudden it's over. And we're like, okay, the computers we have are what we're going to have forever. Okay, so what I started looking at it wasn't necessarily that transistors were the end all. It's just that transistors are what we use today to build computers. Okay? We used to use like vacuum tubes, and we used to use mechanical relays. So it's really just the technology that we're using right now. And so it's an exponential when you look at the advancement in computing. It really is just what's the next thing that's going to happen. Okay? So that's where I started kind of playing around in here. All right, so I had this fascination with what we call reconfigurable computing. And so if you think about a computer chip, it does kind of one thing at a time. But the things it does are really simple, but you have to have them all on the chip to begin with. So if you're going to have an add and a subtract, they both have to be there, even if you're only using one at a time. So everything is on the chip. It's kind of a jack of all trades. It's a general purpose computer circuit, and it works fine as long as you can run really fast. But it's kind of insufficient or inefficient because all that stuff is on there and it's consuming power and it's consuming area and all that sort of stuff. So this idea of reconfigurable computing was that you have a chip that you can configure its hardware to do different tasks. And you could basically have a smaller chip where it's an adder, then you take a second, reconfigure it to be a subtractor, do a subtraction, reconfigure it to be something else, and then it goes, and it can do the same thing as a general purpose computer. So that was the general idea of reconfigurable computing. And this was neat because I latched onto this idea because it's what I did at Hewlett-Packard. It was like, okay, I know how to do this. This isn't a stretch from where I was. Okay, so I started off traditional research at MSU. So I got a little office, hired some students. They went in there, turned the lights off, pulled the curtains down. It was just traditional research. They're sitting at a computer, and it stunk, and it was their pizza boxes, stacked up on there. And we started getting like traditional academic research, which is plots and papers, and we go to conferences, then we go back to our stinky lab, and we repeat it, and we repeat it. So I was at a conference in Idaho, and I gave a talk about the reconfigurable computing that I was working on. And lo and behold, there was a guy from NASA there that I started talking to. And I'm not making this up, over the potato bar, that's all they served. So we had this big potato bar, we're loading our potatoes up, and this NASA guy goes, what you're doing is kind of interesting because it might help with our computers that operate in space. And I was like, what? what? So number one, I'm like, I can't believe I'm talking to somebody from NASA. Number two, they think my stuff might actually help. So I came home from Idaho just jacked, and I was like, this is it. Okay, open the blinds, open the windows, let's get fresh air in here, guys, and let's redo everything because I want to start learning about what it takes to build computers for NASA. So this was at the time when the space shuttle was retiring. So the space shuttle was coming to an end. It was really expensive. They were trying to figure out a way to replace it, and they had this new call for like the type of technology that they needed. So they needed new computers that weren't light, and so I said, well, you know, reconfigurable computing is like that. You use the same little chip for all the things, so it is actually lighter compared to a regular computer. So I was like, I can do that. And it's like, it has to be low power. It's like, well, that's kind of the thing with reconfigurable computing too, is you use like a smaller chip, so it takes, you know, it takes less power because you don't have all that extra unused stuff that needs power all the time. And then it has to have fast performance. It's like, well, that was the idea, right? If you just use a smaller chip, the chances that it can run a little bit faster than the big beefy chip are possible. So it's like, that's cool, I can do that. And then the last one is, needs to operate in the presence of harsh radiation. And so I'm like, all right, I don't know how to do that. So I'm just a computer person. I don't even really know what radiation is other than I get sunburned when I take my shirt off. So I had to now learn about that. So I come back and I start learning about radiation. Well, turns out radiation comes from the stars, right? So you just have this huge ball of hydrogen that sits out there that's the sun, and you got all this hydrogen, most abundant atom that there is in existence, and the gravity pulls it together, and it's like, oh, I got two little hydrogens, this is so cool, and the gravity, there's so much pressure on me, oh my gosh, and then they're like, whoop, we're helium, right? It's like, oh, two hydrogens became helium. The only trick is that the helium mass is like a little bit less than two hydrogens summed together, so that little mass turns into energy, and there was this equation, E equals mc squared, where unfortunately the c was the speed of light, so big energy. You take a little bit of mass, convert it to a lot of energy, and you would think, well, energy's cool, except it's more like a bomb. So when the little two hydrogens go, hey, let's become helium, they go, whoop, boom, and the whole thing explodes, and it shoots every type of radiation that you could ever imagine. Here comes the hydrogen, here comes the helium, here comes the electrons that were orbiting, they got blasted off. Here comes the protons. Hey, some of the nuclei, it actually just blows apart too, so you get that. And you also get every wavelength of electromagnetic radiation there is, okay? So the bomb goes off, blows up. It's cool because it gets heat and it gives, we can live, but it does really send a lot of stuff that makes our computers crash, okay? So that's the big trigger, okay? So now you're sitting there going, hey man, if the sun is so bad, how come our computers work? And it's because of this. The Earth is a dang miracle, okay? I'll tell you that. Number one, the Earth has a churning iron core at the middle of it that creates a magnetic field. And the magnetic field actually deflects a ton of that radiation so that it doesn't just bombard us and, you know, kill us, but more importantly, make our computers crash. It deflects it so it doesn't actually come into us. So it's like, okay, Earth is great. Anything that does get through, it hits our atmosphere and it gets attenuated. So by the time it gets to our computers, it's like, the computers are fine, okay? So Earth is awesome. All right, so you gotta be asking yourself, well, wait a minute. How do computers work in space? I mean, I know there's a space station up there. You know, I've seen people up there and they got laptops. How are those working? Well, it turns out that NASA and the DoD devised techniques to make these chips what they call hardened. So they did all this really cool custom processing of chips, and they were able to figure out how to make the computer resistant to the radiation effects, okay? The trick is this. The reason that our computers don't cost, you know, $1 million each is because they make like $1 million a day. So you have to have a lot of volume in order to get the price down so that we can actually afford them. So the trick with aerospace computers is how many do you sell a year? It's like 2, maybe 5 at the most. So they're outrageously expensive, and the cost has to be covered by like a government infusion of funds at one shot. So they made this one chip like 25 years ago that they use in everything. It costs over $200,000 for one of them, and it basically is as fast as a computer that we had 25 years ago. Okay, so it's basically like the first, less than a penny, if you remember that word. So as an example, Perseverance, which is the latest rover on Mars, used this chip. So did Curiosity, the rover that came 10 years before it. And so did the first mission that was in 2002. Okay, so we're 22 years past and we're still using this thing. So that's the state of the art there. So the whole trick here is like, how do you get faster, but also not cost $200,000 because other people then, like the Department of Defense and NASA, want to go to space. Companies want to put little satellites up there. So we were like, all right, what are we going to do? What are we going to do here? We invented a computer called RAD PC. Okay, I didn't even come up with that name. Some guy at NASA was like, what do you want to call your computer? We're on some flight we're doing, and I go, I don't know. I hadn't even thought that far. And they're like, you have to have a name. I'm like, all right, we'll go think about it. He's like, I'll write in RAD PC for now. And I got home and I'm like, that sounds good. So that was like 15 years ago. Someone named this for me. I'm like, all right, we'll just do it. So RAD PC is what we came up with. And what RAD PC does is you basically use a regular part that you can buy, online. It's not a custom radiation hardened part. And that gets you kind of the fast performance and the low power. Okay? So that's the first part. And then what we do is we can reprogram it, reconfigure it, just like the reconfigurable computing thing that I was talking about. And it turns out that if you reconfigure it, you can actually flush out some of the problems due to radiation. So the radiation is flying through, and the radiation we're caring about is the ones where it goes straight through the chip. Well, it flips like the computer into a state that it crashes. So what we do is we watch that and go, hey, we just got hit. So then it goes, let's reconfigure that little part that got hit, and all of a sudden it puts it back to its first state, and then it starts working again. So that was like our magic. But you had to also have like extra copies of the computer. So it turns out that if you think about it, let's say you had 3 computers that were identical, if one of them got hit, you could still produce the right answer because you have a majority vote. So if you took 3 computers and voted on the output, it would be right. Okay? So it's like, okay, well, we need at least 3. Turns out we used 4 because we figured out that when you had 4 computers, you could have one that went down, and then while you're trying to repair it, you would have another one that could go down, and then the first one came back up and you would be set. Okay? I actually had a PhD student that was their dissertation. I was like, we need to find the optimal number of processors in our RAD PC. And so he spent 5 years, did all these experiments, and he came in and he just slaps it down on the desk. He's like, 4. He's like, congratulations, doctor. And that was it. That was his whole dissertation. It turns out if you use more, then the area gets so big that you're more susceptible to the radiation, so then more things start crashing. It doesn't work. 3 isn't quite enough. 4 is the optimal number. So he got a PhD out of that. Okay, so the thing is like, okay, we have this idea. Let's get back in the lab. Okay, close the windows. Let's sync this place up. Let's start getting data. So we started doing simulations on this. Looks promising, but the key was this was for NASA. And this is where everything changes for me, because NASA is not about papers and simulations. They want you to fly it. So they said, all right, that's cool. Let's get you flying. And what they do is they have this thing called technical readiness level, and that is a scale from 1 to 9, where 1 is an idea in your head, 3 is like you've actually written it on a whiteboard, it kind of makes sense. 4 is where you start building it and testing it. So they said you need to start building little payloads and flying them to get up to 9, which is where 9 is like it's a product that somebody has actually used. So RAD-PC started as 3 in the lab, and we're like, we need to get to 4. Okay? So we started trying to test it on the ground first to show that we can actually get funding for flying. So we went down to Marshall Space Flight Center, we loaded up all our suitcases with it, showed them a proof of concept where we tried to induce radiation with a laser pointer. So we're sitting there doing this, and we had this sensor going, well, look at how it crashes and then recovers. And then NASA people were like, well, you're using a laser pointer, that's not what's in space. And it's like, well, just pretend. And they're like, okay, we see what you're doing. So they said, if you're going to try to prove to us that you need money to fly, hit it with something hard. Okay? So then we went to the Texas A&M cyclotron. Okay? Horrible place, don't ever go there. Very expensive. You go, it's this giant building, as big as this high school, and they accelerate particles. Okay? So then you go down on the ground, 20 feet below the ground, it's all concrete, and then you put your little experiment there, and then you run back upstairs, and then they hit you. And they hit us, and it seemed to work. Okay? So we were like, okay, we did radiation chamber testing, so now what can we do? And it's like, all right, start flying. So one of the simplest ways to fly is a high altitude balloon. Okay? You can actually do this with like just big balloons that like the car dealerships use. We actually have a ballooning program at MSU called Borealis, and they basically take this huge balloon from a car dealership, tank of helium, they tie a rope to it, fill it up, duct tape the rope to it, and then they let it go up a little bit, and they tie an experiment to it, and then they let it go. And then they go out and they watch for it, track it with like a GPS thing, and then they go find it, it goes up, pops, comes down, parachutes, and then it usually lands in some rancher's field, so you gotta go up to the rancher and be like, can I get my balloon? And they're like, get out of here. You're like, we're from MSU, and then you're like, okay, go. So then you go get the payload, look at your data, everything's cool. So we did a bunch of those, and this picture right here kind of shows what it looks like. These are people, and that's the balloon. So you can see them just like letting it go up in the air. So then we did a bunch of those, we did 8 of those, and then NASA started letting us fly on bigger balloon systems. So this one is a little tricky to see, but this right here is a balloon. That's a semi. Okay, so this balloon is like as big as, it'd be like as big as this building when it starts going up into altitude, multiplied by like 10 stories higher than this. Okay, so they're just absolutely massive. And they actually get up to the darkness of space. So on the right here, this is actually what it looks like when you get up there. You're not in technically space, but you're outside of most of the blue of the atmosphere. So it's actually way up there and you get hit with radiation. So then they said, okay, that worked, let's go higher. So then we did what they call sounding rockets. Sounding just means you go up, come back down. But sounding rockets are like a rocket. It's not a rocket, it's a missile. So they use the same missile bodies as like just regular missiles. And we did a couple of these flights. And so you kind of see here, it's like, this is how big they are. They're like 30 feet high. This is us standing down there. Our payload was still simple, where it was just, you didn't need to know that much about aerospace. You just needed to be able to build like a thing, okay? So we built our thing, put it in there. First one we did, this little guy right here was like a stack of little computer boards. Just crushed it, just completely crushed it. There was so much force, we got it back, and it's just like, where's our experiment? And it's like, that's it, it's now a pancake. So then we had to learn how to like build it so it's a little bit stronger. And so we ended up flying, and it was cool, and it was like, we kind of did it. But you're only in space for 12 minutes before you come back down, okay? So then NASA said, all right, I want you to go to the International Space Station and act like a real payload. And I was like, okay. Once again, I have exceeded my knowledge of the field, so I'm like, I have no idea how to build something that actually operates in space. RadPC was just a cool idea that I had. I didn't think I'd get this far. So we're like, how do you do it at this point? Now you need so much knowledge, you can't even do it by yourself. So I started collaborating with a couple people that work in this lab we have at MSU called Space Science and Engineering Lab. One of the things that MSU greatly benefits from is people retiring from big cities, coming to MSU and wanting to do kind of a retirement job, and they'll spend 20 years working for MSU, don't necessarily need a big paycheck, they have a world of experience, and they just want to help. And it's like, so we got a couple guys that work for Lockheed Martin that kind of retired here. They work full time, but they don't even look at it like a job, it's just fun. So I started collaborating with them. These are the guys, SSEL is the name of the lab, where these are the small little satellites you hear about the most often in the news. It's like, MSU put a satellite up there. Well, these are the guys that do it. So I was like, okay, I need to go into space. Can you help me out? And so they helped me out. So we started off, let's see if I can play this. We built a payload, and we launched it from Japan, of all places. It just happened to be where it was. And so this thing went up to the International Space Station. And the way it works is it goes up in like a crew transport bag, and they actually then just take it out, and the human beings install it. So this is it. This is the first payload that's actually in the microgravity of space, and you can see the MSU logo right there, and that's our little astronaut buddy who's installing it for us. And we went up there for a year, they plugged us in, and it actually worked. And so it was like the coolest moment that I've ever had. I was at Old Chicago's, and they sent me this video, and I'm just like shaking, and beer's all over the table, and my wife's like, are you okay? And he's like, look at this video! And it was like the sweetest moment, one of the sweetest moments ever. And so then, it's like, okay, now what? Well, you don't get to test it in the nice little confines of the space station anymore, where you got unlimited power and humans. You gotta be on your own. So we got funded to build 2, what we call small satellites. Small is like the size of a loaf of bread. Actually, exactly the size of that about, except it's kind of rectangle. Okay, so we endeavored to build these 2 little satellites, and that's what it looks like. Okay, so it's the size of a loaf of bread, and I want you to notice that this is the M on top of Montana State, And this is us doing kind of the final. This is me and a graduate student, Skylar Tamke. We went down, after it was all built, and we integrated it with, the little launcher that goes up there. And the way that you put it into orbit is it goes up in a little bag, they put bubble wrap around it, fly it up to the space station, and then what they do is it's in a spring-loaded box, and then they take out the airlock, and the robotic arm of the space station grabs it, and they point it, and then they go, boop, and the door opens, and the little thing like pushes out with a spring, and they push you down into the earth, so you orbit for like 2 years, and then you burn up. So it's like nothing hits the ground. You can't use like a real heavy metal, but aluminum melts and everything's cool. So that's what it looks like coming out of the space station. But I want to point your attention to this. This is the M of MSU coming out of the International Space Station, going into orbit, and we call this Rad PC demonstration Rad Sat. And then it goes, and it goes, and it goes, and life is good. So then we got our second shot. A bunch of stuff worked, a whole bunch of stuff didn't work. We fixed what we could, and we built another satellite. This time we're like, all right, let's do the cat head. So there's the cat head. This is Chris Major, got his PhD under me a couple years ago. Same facility in Texas where we put the thing in the little spring-loaded box, and we went out there, watched this thing launch. Sweet launch, beautiful day. And there it goes again, out of the deployer and into orbit. Oh, if you didn't see it, there's the cat head, and there's the cat head, there's the cat head, there's the cat head, and we're off and running. So we basically have hit the pinnacle. We've been in space, we've been in low Earth orbit. This is so fantastic, and so it's like, well, I guess that's it for being a professor. What do I do now? It's like, oh my goodness. I got called by NASA at home. Now that's something. As a professor, I've never been called like by anybody. Like no one calls us, let alone somebody you propose to. And then I get called from NASA on my cell phone at home to tell me that we were selected to go to the moon. And I'm like, this is weird, but again, I was almost having a panic attack. So anyway, we got chosen to go to the moon, and that started about 5 years ago. That was in 2019 is when we got that call. So the RAD-PC mission right now that I'm working on currently is to try to put this thing on the moon. Now, I'm not doing it. I'm working with a company that will do it. And this kind of falls into the whole, like, what are we doing in space right now? Space Shuttle did retire. You notice SpaceX is launching like crazy. And we're talking about going to the moon. You probably heard the words Artemis. But when we go back to the moon now, it is not to go pick up a rock, hit a golf ball, and then come right back home. It's to go to stay, because it is going to be a launching point to go to Mars. So we want to start going to the moon and start building up stuff, places to live, places to store stuff, and then we use that to launch and go to Mars. And so when you look at the whole kind of plan to get to Mars, one of the plans is to drop stuff on the moon, not using crewed landers. So it's not like Apollo where somebody is actually in there. It's a robot lander, and you try to get it to land, and the idea is that it starts just dropping off cargo. So it drops off a robot that starts building a house for you. It drops off a robot that starts making water. It drops off a robot to start making rocket fuel. And so then the humans come, they're like, okay, well there's my water, there's my house, and I'm ready to go. And then they can start doing other stuff. So we got selected to go on one of these commercial lunar payload services landers, and they said, okay, you're going to work with this company called Firefly, and you will build your little payload, and you will put it on their thing, and then they will go there, and you'll work with them to get your data back. Okay, so that's what we're looking like. The lander is not enormous. It is like this. It's probably 8 feet tall and maybe 8 feet wide. So it's not huge, and it actually can get there on just a SpaceX rocket. So it goes up, and they're not going to do the 3-day. They're going to do like these elliptical orbits. So they'll do 4 like big ellipses around the Earth to try to use the gravity of the Earth to try to speed up, and then they'll like, woo, and then they'll go around the moon, and they'll slow down, and then they boop, land on the moon, and hopefully it'll work. Okay, so this is the lander last week. This is what it is. It's done. It's built. It went out to JPL, Jet Propulsion Lab in California, and they put it in this giant chamber, and they heated it up, and they pulled all the air out, and then they shook it, and they said, hey, looks pretty cool. If you notice, that little square that's sticking out of that little gold like blanket is our buddy, RAD-PC. So that's what the payload looks like that will go to the moon, okay? This is about a mock-up of it, and it's not very big. It's the size of like a little bit bigger than a Rubik's Cube. It's like half of what our little satellites were. And so it's not huge, but it is pretty cool. We came back from seeing like a mock-up of the landing, and I hired a student, and I said, I have to have a mock-up in the engineering building. I want everybody to walk in here, and I want them to see a mock-up of a lander, and we can tell everybody, we're going on this lander. I need this right now. And he's like, you got it, boss. And he like spent just months and months, and he keeps like, I'm 3D printing it, and everything's so great. And I'm like, oh man, I can't wait to see it. And he texts me a picture of it. This is the picture he texts me, and it's late at night. I'm like, dude, I want this tomorrow. Like, meet me 8 a.m. And he's like, how about 10? I'm like, fine. So we meet, and he shows me his lander that we're going to put in the lobby of our big engineering building. And I'm like, it needs to be at least 3 times bigger than that. I don't think this is what we want in here. So anyway, so now you think about where we're going. We are going, one of the coolest parts about this is we go to a place that you can see with the naked eye, and it's in what we call the Mare Crisium, which stands for the Sea of Crisis. But don't worry about that. But it's actually over in the upper right hand of the moon. And you know, the moon is like, the face we see of the moon is the face we always see. It just happens to be like it never, like, it's not rotating. We don't get to see the backside of it. So we will always be able to see this thing. And this is going to be pretty dang awesome because it will be there forever. We're not coming back. This is a one-way trip, and even if it crashes into the moon, someday somebody will go up there and they're sweeping up the moon, like, man, there's a lot of junk up here. What's this thing? And there will be a rad PC sitting there, and they'll go, is that the logo from MSU? Okay, one of the things we did is said, okay, if some future human or humanoid gets there and wants to look at this thing, we should have some memorabilia inside of this thing. So one of the things we did to kind of engage other people in there is we invited everybody to put messages inside of the computer. So we have a bunch of these little SD cards in there where students, teachers, anybody can actually upload messages. Many of you maybe did that, or had students that did that, because we sent it out kind of a statewide blast, all the high school and middle school, actually all the K through 12 teachers. And so we put messages from everybody. We actually then went and got video messages from, you know, our governor, our president of MSU, senators, our congressmen. We had a bunch of news stories about this, and it got people excited. They could upload messages, and it was really cool. We put every edition of the MSU newspaper going back to 1895 on this thing. So it's got, when the next person opens this up in like 10,000 years, they're going to find a lot of cool stuff. Also has economic benefit to our valley. We actually started a company 2 or 3 years ago called Resilient Computing that is trying to take rad PC and commercialize it. So one of the students you saw that was working on that satellite, he's the first employee, and he actually has now a buddy over there. So I got 2 PhD students from MSU that are actually trying to build the little computer so that if you wanted to buy one, you could. Okay, so it isn't just papers. So now the key is like, okay, how are you doing this? I mean, you must be really, your hands must be tired, you know, from all the building and stuff. Turns out, as a professor, I don't do much. What I do is I try to work with the agencies like NASA. I'm like, man, it'd be really cool if we did this. And they're like, oh, okay, let's see if we can do it. And they kind of fund the projects. Then I turn around and hire students to do it. And then I go back and beg for more money. And then if I get money, I give it to the students. So every single thing has been done by students. And the students have been PhD students all the way to freshman engineering students. And we've had physics students. We've had art students on this. But everything is, I've never turned a screwdriver since becoming a professor. I've never soldered anything together. I just get the money, give it to the students, and that is it, okay? If you wanted to do one of these little thingamajigs, there is actually an opportunity. NASA has this program called Tech Rise, and what they do is they want to engage between 6th to 12th graders in flying something. So they have this program where you can actually apply, and it's not a lot of money. They'll give you like $1,500 to try to have a student club or student group or a student class build a little payload. And this year's competition will actually go up on a high altitude balloon. So you actually go up to in the darkness of space, and then you float for like 4 hours, and then you come down. And so the deadline for the application is actually November 1st. Hopefully this isn't being recorded, but I'm just totally kidding. NASA has told me that Montana is like the only state that hasn't won one of these, and their goal is to have all 50 states participate at one time. So if anybody wants to do this, your chances of winning are greater than 0. Okay, and that's pretty good. All right, so now, how does that fit into education? So I thought that's the story of the MSU Moon Computer. It is going up, hopefully, in December. We are doing simulations right now where we're on our console with our headsets, and they say stuff to us like, RADPC, this is mission manager on MP1, ComCheck, and I'm like, this is RADPC, NASA 5x5. I mean, we have to learn all these wacky ways to talk like the military. And we're using the simulator to try to learn how to run the thing. In 2 weeks, the real lander comes back to Austin, and we're going to do 5 days, 24 hours a day, talking to the real lander. So I'm building up, what I do right now when I go to work is build up computer stations and get the software ready so that we can staff this for 5 days round the clock with people to sit there and listen for them to call RADPC and check whether our data is going. Okay? So it's hopefully going to be like February when we actually get this thing on the moon. So how does this tie into education, and especially high school education, or actually K-12 education? So I thought I'd close with just kind of some of the trends of what's happening in engineering education. Okay? So right now, there's a lot of talk about 4 kind of main topics. One of them is pathways into STEM. So pathway is kind of a new word where we don't like to call it a funnel anymore, because that says you start with what you do, this big group of students, and then you whittle it down, and then you're out of there. So there's 2 problems with that. What happens to the people that fell out of the funnel, number one, and what happens to people that want to get back in further down the funnel? You can't, you have to go back to the top and go back down. So everybody's trying to figure out different pathways into careers that require engineering or scientific or computational thinking, and it is possible that that person might not have to take 4 semesters of calculus. I said it. Okay? So that's what everybody's trying to figure out. How does the MSU Moon Project tie into that? If you were a teacher listening to this and you thought, I might talk to my students about this. Number one, you could go rockets, space, and you're going to get a group of students excited. And I'm here to tell you that the research we've done for 20 years, 40 years, all the research on those students that got excited, they were going to become engineers anyway. Okay? All you did was get them more excited. Okay? So how do you reach the people that this doesn't excite? So number one, they've kind of learned that there's groups of people that enjoy working with other people and helping other people. I know, shocking. So it turns out that if you can make the message about how does this help society, you might recruit different types of people into that. It's not that anything changes, it's just that you explain it a little bit differently. Okay? We have degrees at MSU. We're all excited right now because we have departments in the College of Engineering that now have over 50% female students. So we got more women than men. So how'd you do that? Well, we just had to change the name of the degree. It's now biomedical engineering, and we got 50% female engineering students. Right? It's kind of like a messaging thing of how do you tell them what we're doing is actually important to society as opposed to just blowing up rockets and doing cool stuff like that. Another thing that I always like to highlight, though, is try to help your students realize there is stuff going on in Montana. There is stuff going on. There are jobs here. There are high-tech jobs. There's fun jobs. There's interdisciplinary jobs. You work with other people. You help people. And we're trying to build this kind of state economy that has those good jobs. Here's kind of what's happening. The economy's building up, especially in Bozeman. And what's happening is we got a lot of good jobs. But what's happening is they're being filled by out-of-state people. So they're like, oh my gosh, I can finally move to Montana and get a high-paying job. And we're like, no, that's what we didn't want that. We were going to hopefully get our own Montana-born people to take those jobs. And so it's letting the Montanans know, it's like this stuff is happening. Obviously you can't keep out-of-staters from coming here and taking the jobs, but we can encourage Montanans to apply for those jobs. So letting them know that opportunity is here is one thing, okay? All right. The other thing that's got people freaking out is everybody's going, the number of high school graduates is going to decline in our country over the next 10 to 20 years. People are freaking out about this, okay? So it is true, this is gonna happen, and everybody's like, colleges are gonna get wiped out, we gotta get ready to fire everybody, So it's gonna happen. I will tell you this, This was also going to happen in 2007, so when I first started at MSU, our first faculty meeting was, the number of high school graduates in Montana is declining. Get ready for layoffs, get ready for layoffs. I mean, our dean, our provost, our president, it's like, it's over, we're gonna wipe out full departments. And as soon as they left the room, we started on 12 years of exponential enrollment growth countrywide, and nobody knew why it was happening. Turns out later it was the Great Recession, everybody went back to college, but it wasn't traditional students who came back. They wanted engineering, they wanted nursing, and so predicting the future is hard. So I've heard this story before. Who knows if it's going to impact us? I think what might happen, what people are kind of saying is like, don't worry so much. There's going to be a consolidation of universities, okay? For-profit universities that aren't your top, like Harvard's, they're going out of business fast. Like 60 went out of business in 2023. There's going to be a consolidation. Who knows what the future is? I think it's going to be okay though. Okay, so that's something that's on everybody's mind. The other thing in higher education that's on everybody's mind is the public perception of a college degree. You've heard it on the news, everybody's complaining, you go to college, it's worthless, you take on all this student loan debt. It's like, is it worthwhile? So the problem is, you look at the perception that people have that's shaped by basically politics, to be honest with you, and it's less than 50% of it thinks that it's worth going to college anymore. The higher education has a 60% negative impression. The impression that polls show of higher education, 60% of it is negative. That was 50% 1 year ago. Now we're in an election cycle, so that's probably why, but think about that. Think about a new culture where people just look at higher education and go, you're supposed to look at higher education and go, yeah, I can maybe do that. But it's like, that's something that's going to impact you. And then the final one that's got everybody freaking is AI, okay? So, artificial intelligence. If you follow artificial intelligence, you'll lose some sleep, okay? It's really amazing what can be done with artificial intelligence. What is happening in engineering education is this. We are talking about what does it look like using artificial intelligence in a 4-year college degree, okay? Here's the way the typical degree works in engineering. You start off, you take classes that are really exciting, you get jacked up about the degree, then you go into the middle 2 years, and it's like we don't like to do it, but it is, it's like a weed out period, okay? It's the grind. They get into those third and fourth calculus classes, they're taking circuits, if you're going to engineer mechanics, it's where people go, this sucks, I don't want to be a part of this anymore, and they leave. And so you see people, we don't like calling it weed out, but they choose out of engineering. So now you go, artificial intelligence is just like the computer, and before that the calculator, before that the slide rule, but we have access to all the information in the world now with the internet, and now we have a way to interpret it. So maybe, just maybe, we don't have to push students through the grind. So maybe they can kind of just say, okay, I'll learn the tools to do the grind in the second and third year, and then get to the application in the fourth year. So the discussions around this are, well, that's unfair, I had to go through the grind, that's one discussion. Another discussion is, so if you don't go through the grind, can you evaluate what comes out of AI intelligently to know that it's a good solution or not? Or do you have to go through the grind to be able to understand the output of AI? Okay? Because bridges fail, people die. You can't have them fail, right? And so those are the discussions that are going on right now. Now, technology and education helps with, when you look at Maslow's hierarchy of basic needs, it's like we always use technology to live. So it's like, we need food and shelter. Well, we use technology to farm and get food and everything. It's like, we need water. We use technology for that. And you go up to the point where you're like, you wake up and you have nothing to do but worry about self-esteem. Oh, right? It's like, is that good? As a parent, it's kind of like, if you skip over all the hard work and now you're like, oh, I'm just working on my self-esteem. I don't know about that. So those are the things that people are talking about in the future of engineering education. I think they're all good. They're all real. It's very hard to predict the future, but it is, I would say, an exciting time to be alive. So, all right, with that, I will end and I will answer any questions that you might have on this, but I appreciate you listening to me.